All right, so let's start cafe April session. Welcome to cafe. I'm Kellie Kubota, Ohio State University. I'm the host of the Indoor Ag Science Cafe. I really appreciate you are connecting today. Such a difficult time with this pandemic situation. But I like to keep going and supporting everyone who is trying to make the difference in a controlled environment agriculture. So let's take a few minutes before starting today's topical presentation, as usual. So we have two parts usually in a cafe, monthly cafe, and the idea of the cafe is to communicate among professionals, and then also academic, professors. And then we have today Dr. Roberto Lopez and Kellie Walters from Michigan State University talking about quite interesting research using basil, flavor, and photons. And then after that, we are going to open up for discussion. Typically, this time is questions regarding the presentation, but it doesn't have to be like that. So you can ask any questions you wanted to ask. All right, so there are two other opportunities for you to ask questions in general, or anything you come up and then wanted to just write up. So one is the Indoor Ag Science Queries website. And then this link is always in email, I'm sending from MailChimp software. So you can find that and then click on, and then identifying yourself is optional. So you can put any questions without identifying who you are. And then some of the questions is just, everywhere, but I'm hoping to answer these questions in one of the future cafes dedicated for answering questions. All right, and then the other one is the Q&A forum, which is Good Ag Site or Public Good Ag Site. It's special forum dedicated for Indoor Ag Science Cafe community. So that link is also in the email. Upcoming cafe series after today, May 26, 11 a.m. Eastern Time. Nicola Kerslake is going to talk about how to fund your indoor farm. And then June, this is also Tuesday, 11 a.m. regular time of our cafe. Dr. Eric Ranko is going to talk about either his research or some educational contents. We are still discussing on that content, but he's gonna give another talk. Everyone knows he's from Michigan State University. And in July, we will not have any cafe because it's summer and conference time, hopefully. And then August. All right, so let's stop my sharing here and then have Dr. Roberto Lopez. Can you see that?
Yes. Can you see my screen?
Yes.
Okay. Well, thank you very much, Sherry, and good afternoon to those of you on the East Coast, and good morning to the rest of you. So today, Kellie and I are basically going to give you a little snapshot of the work that Kellie has been working on over the past 4 years. This is just part of her dissertation, and we've really primarily focused on basil. And why are we focusing on basil? Well, basil is obviously one of the most popular culinary herbs that is used. But part of her research really wanted to determine how we could improve yield as well as the quality. And then, of course, one of the important things that we often forget about is how does this impact the flavor and other compounds? As well as how does this affect the consumer preference of basil itself? And actually, basil is probably one of the best culinary herbs, in our opinion, to work with because of the aroma, the flavor. It can be used, obviously, in a wide variety of dishes. Here, we have an example of pesto. With production, most growers know how to grow basil. Obviously, it requires quite warm temperatures, high light. But interestingly, basil also has quite a few post-harvest issues, and primarily one of those is chilling injuries. We can see in this photograph when basically basil is placed at temperatures below 50 degrees Fahrenheit, we start to see symptoms of chilling injury. So our overall goal of this research was to improve crop quality while maintaining yield. And as I mentioned before, basil is very popular. You can see in terms of return, you can get quite a high price premium for only, let's say, 1.5 ounces. So the objectives of this research were really to determine how light intensity and carbon dioxide concentration influence sweet basil seedlings. So this is all done indoors, not within a greenhouse, to then look at how it affects the growth and development, volatiles, as well as the consumer preference. So we started off by basically looking at seedlings at the seedling stage all the way through finishing. So again, our overall goal is really to increase that volatile content. And so we started off by basically having a nationwide survey where we asked growers a variety of questions. And one of the questions we asked them is how much would research on manipulating the growing environment to improve crop flavor benefit their operation? And surprisingly, we found that over 50% said very likely, and about 40% said moderately. So this is one of the primary reasons why we decided to look at flavor and how it's influenced by the growing environment. We also asked if their customers would be willing to pay more for that increased flavor. And 84% of the producers indicated that their consumers would be willing to pay more. So we started off by basically growing basil seedlings in a walk-in grow chamber. And we grew them in rock wool cubes. We maintained an EC of about 0.78, which gave us 100 parts per million nitrogen. We maintained the pH at around 6. The seedlings were grown, again, with an average daily temperature of 73 degrees Fahrenheit or 23 degrees Celsius. We had basically 4 light environments, anywhere from 100 all the way up to 600 micromoles of light, to give us daily light integrals that were anywhere from 6 moles all the way up to the very high end of 35 moles of light. Again, we were trying to push the envelope to see how we would influence the overall volatiles and flavor of the basil. So these are the actual light intensities that we were able to achieve. So about 109 all the way up to 617 micromoles of light. Here's our light spectrum, so you can see the overall photon flux density. So why did we choose to basically look at lighting seedlings versus the finished plant? Well, think about this as being the area that a finished plant takes up. Now, obviously with seedlings, we can light a lot more seedlings than we can a finished plant. So in terms of the input cost, our overall goal was, can we provide seedlings with increased light intensities, and how is that going to influence the flavor compounds both during the seedling stage as well as during harvest? So these are our basil seedlings. So we worked with Nufar. This is 2 weeks after sowing, under our target light intensities of 100 to 600 micromoles. As you would expect, with increasing light intensity, we have obviously increased rooting. We have a much larger transplant. So again, not too surprising. Here again is each individual tray, so you can see increasing that light intensity. We have obviously an increase in our canopy coverage, and those seedlings are ready to transplant faster. So we see our overall shoot dry mass increases with increasing light intensity, and we see about a 280% increase in shoot dry mass just by increasing that light intensity during the seedling stage for 2 weeks. What about leaf area? Well, again, we saw a very large increase in leaf area, about 738% increase just by increasing that light intensity. So now let's move on really to I think the most interesting part of the study is how are volatiles influenced, and what are those volatiles that we're most interested in. So there's a wide variety of them. So we have eugenol, and eugenol is basically what gives basil that aroma of cloves. We also have methyl eugenol, and these are part of the phenylpropanoids. Then we have methyl chavicol, which gives basil that aroma of anise. And again, this is another phenylpropanoid. And then we have 1,8-cinnalol, which gives us that aroma of eucalyptus. This is a monoterpenoid. And lastly, we have linalool, which gives us the aroma that's often referred to as a floral spiciness. And some folks actually think that it smells like Fruit Loops cereal. So this is, again, another monoterpenoid. So with all of these volatiles, really our goal was to determine if temperature, light intensity, and carbon dioxide concentration would influence them. So with that, now I'm going to hand it over to Kellie, who's actually going to talk about what she found.
Thanks, Roberto. So for this talk, we're just focusing on light intensity. And what we found was that as we increased the light intensity from 100 to 600 micromoles, so again, this is a 16-hour photo period, daily light integrals from 6 to about 35, the concentration of linalool increased linearly. So if we look at the next compound, 1,8-cineol, again, these are both terpenes, so they're both monoterpenoids, and we see that same linear increase of the concentration with an increase in light intensity. But when we move on to eugenol, so this is a phenylpropanoid. We have pretty similar concentrations in the eugenol concentration from light intensities from 100 to 400 micromoles. But as the light intensity further increases up to 600 micromoles, we see a pretty large increase in the concentration of eugenol. So that basil is going to taste much more clove-like and have a much more pungent flavor. So if we look at these all together, we see again the two terpenes have a linear increase. Eugenol has a quadratic increase, mainly just at that highest concentration. So you may notice that I did not include methyl eugenol because in this study the concentrations were fairly small and there was a lot of variation, so there were no significant differences. And methyl chavicol, or that anise or black licorice compound, so we did see trends that they increased as light intensity increased, but there was so much variation that it was not statistically significant. So again, this was all at the seedling stage. So what happens if we take these seedlings and transplant them into the greenhouse for finishing? So we transplanted them after 2 weeks under the light treatments into the greenhouse for 3 weeks into deep flow technique hydroponic systems. So now they're all grown in the same environment in the greenhouse with an average daily temperature of about 72, a daily light integral of about 14 moles. So that's kind of similar to the 200 micromole 16-hour photoperiod treatment at the seedling stage. That was about 12 moles. And then the pH and electrical conductivity were adjusted daily. So what we found, as you can see in these pictures, was that the differences persisted through finishing. So fresh mass, for example, had about an 80% increase as the treatments at the seedling stage increased from 100 to 600 micromoles. So plants grown under 100 to 200 micromoles, pretty similar, and fresh mass, 400 to 600 micromoles were pretty similar as well, but much larger increases in fresh mass. So if we can increase the light intensity up to 400 to 600 micromoles at that seedling stage, it may seem high, but you see increased yields later on. We also see an increase in branch number, so not just growth, but also development. You can see those grown under 100 micromoles at the seedling stage had about 4 branches per plant, while those grown under 600 micromoles had about 6 branches per plant. So when we compare the flavor, or some of the secondary metabolites, we see that some of the differences persist. So for eugenol, we see a pretty similar trend. So that bottom darker green line is the eugenol concentration at the seedling stage. And that lighter green line is the eugenol concentration after 3 weeks in the greenhouse. So there is still a significantly higher concentration of eugenol in the finished plants that were produced under 600 micromoles when they were a seedling. So you do have some carryover of that flavor. But the other compounds, so if we look at 1,8-cineol, you can see that linear increase, again, at the seedling stage. But if we look at the finishing stage, there was no significant difference in the concentration. And so I didn't include a graph of the linalool, but it is a similar trend. And this may be due to, so these are both terpenes, 1,8-cineol and linalool, and eugenol is a phenylpropanoid, so different biosynthetic pathways. So these are, what we find in the lab. So we use gas chromatography mass spectrometry to quantify these volatile compounds that give basil, its characteristic flavor and aroma. But what do these numbers actually mean? Our end consumer is, normal people who are eating the basil. So it really doesn't matter what the concentrations are if consumers can't perceive the difference, or if they don't like the difference. So what we did was we worked with the Consumer Sensory Laboratory here at Michigan State. And this is a look behind how we conducted our consumer sensory panels. So we had the different samples set out, and then there was a computer screen, and each panelist had received their samples in a random order, and it lit up when the workers in the back had to give the panelists a new sample. And then if we look at, this is again behind the scenes, there's these little sliding doors where the workers in the back slid the samples through the doors to the panelists. And the panelists sat at computers, so they received their samples, they had water and crackers and then their basil leaves, and they tasted the leaves and they answered a series of questions. So what we found with this was that overall, consumers preferred the basil that was grown under 200 micromoles, especially compared to those grown under 600 micromoles. But why? So as we delve into this, we can see that color, texture, flavor, and aroma are all contributing. So first, we'll look at color, texture, and flavor. So those purple, blue, and red lines, you can see they're greatest under 200 micromoles. So for color, we'll delve more into how we know some of this when dissecting some of the words and comments the consumers had. But the 200 micromole treatment had a brighter green color. It wasn't dull or faded. As you increase the light intensity at the seedling stage up to 600 micromoles, you see that there's some damage to the leaf. Now, when we grew the plants, we didn't see any damage to the leaves, but as soon as we rinsed the leaves, regardless of how gentle we are, there tended to be bruising, and the consumers did not like that. The texture, they preferred the texture of the 200 micromole treatment because it was nice and crisp. There were small, crisp leaves. As the light intensity increased up to 600 micromoles, the samples began to wilt more quickly. And the flavor. So the flavor under 100 micromoles was rather weak, and the consumer said it didn't have that characteristic basil flavor. They couldn't really tell. As light intensity increased to 200 micromoles, it was that characteristic flavor of basil, but under 400 or 600 micromoles, it was much too strong. And they started making comments about the cloviness or the anise or licorice flavor of the basil. Now looking at the yellow line for aroma, 100 micromoles, it didn't have a very strong aroma because again, it didn't have that many secondary metabolites or volatiles. As the light intensity increased, to 200 to 600 micromoles, it had that characteristic basil flavor that the consumers were looking for. And it's much more difficult to have too much smell than it is to have too much flavor. So then we look at the leaf size. It's pretty apparent that the size of the leaves are different. And they really preferred the larger sizes of leaves. Now, these are 2-week-old seedlings. The smallest one is about the size of my pinky nail, so it's pretty small. But overall, again, they like the larger size of the leaves. There were some comments, though, about, oh, the little ones would be perfect. We could throw it right in our dish and we wouldn't have to cut them up. So it just depends. So then we're growing sweet basil, so we want our basil to be sweet. But we also had them evaluate on a scale of extremely bitter to extremely sweet. So these are both Likert scales. The previous one was how much they liked it or disliked it. And this one is extremely bitter to extremely sweet again. 100 micromoles, it didn't really have much of a flavor, so it was a pretty neutral sweetness, bitterness. 200 micromoles, slightly sweet, so it had that sweet characteristic we're going after. Those grown under 400 or 600 micromoles, it was slightly bitter. So then we look at all the comments. So for this study, we had 90 participants. So we had a lot of different comments about what they liked, what they disliked, and their overall comments. So the larger the letters here, the larger the words, it corresponds to a greater frequency of that word in the comments. So this is what we found overall. But let's dissect it between our different treatments. Roberto? Okay. So 100 micromoles, we see the biggest words were small, a small size, and then there were comments on the color. As we increase the light intensity to 200 micromoles, small gets a little bit smaller and the word strong appears, and there are more comments about the aroma. And we start to see the word bitter. As we increase the light intensity of 400 micromoles, bitter becomes much more prominent, strong, and there's comments on the texture and the size, probably because it's bigger than the 100 micromole treatment. And the comments for 600 micromoles were bitter, strong, aroma, size, color. So another thing that I would like to point out is the word licorice. It's a little bit smaller in there, but the licorice, people really pulled out that methyl chavicol flavor. So that was really prominent. And we're not going to talk about it too much here because I haven't delved into it too much yet, but different compounds have different odor or taste thresholds. So you may have the same concentration of methyl chavicol and linalool, but you may perceive the methyl chavicol much more than linalool. So if we statistically analyze all of the comments, so we used a chi-squared statistical analysis, and these were all significant with a p-value of at least 0.05. And significantly different between the different light intensity treatments. So if we look at the top here, first look at the light intensity treatments. The comments for the 100 and 200 micromole treatment were more similar to each other than the 400 or 600 micromole treatment. Now the colors of this figure correspond to the frequency of the comments. So the lighter the color, the more frequently that word was used. So bitter, you can see that under 400 or 600 micromoles, the word bitter was used more frequently. The words by, spice, enjoyable, subtle were used most frequently for the 100 micromole treatment. As we mentioned multiple times, small and tiny, 100 to 200 micromoles was the most common. Mouth, an interesting word, reminds quickly, yellow, were most commonly used for the 400 micromole treatment, whereas vibrant, so a more vibrant color was used for 200 micromoles. It was a more vibrant green. And then brown, wilted, spicier, odd, chewy was most commonly used for the 600 micromole treatment. So if we move on to what they liked or disliked overall, regardless of the treatment, the words color, size, strong, and texture were used to describe what they liked. And what they disliked, bitter, small, aroma, strong, and aftertaste. So again, if we analyze these, there are a lot of different words that are significantly different between like and dislike. So first, let's pull out some of the texture associated words. So texture was most commonly associated with liking. So what they liked about the texture was the crunch, crunchiness, but they didn't like the leaves that were wilted. Regarding the size of the leaves, they disliked small leaves, liked large leaves. For the color, they liked bright green leaves and disliked pale or yellow leaves. And then finally, they liked the sweet basil and they disliked the bitter characteristics.
Okay, so what can we take out of these studies? Obviously, that increasing the light intensity to 600 micromoles resulted in increased fresh mass and leaf area during the seedling production stage. We also found that during the seedling production stage, we obviously had an increased flavor compound concentration, as well as an increased fresh mass after finishing in the common greenhouse environment. Interestingly, we also found that eugenol, which basically gives us that clove aroma and flavor, concentrations also increased during the finishing stage. Also, that we found that light intensity influenced the bitterness, some of the aftertaste, obviously the color, texture, flavor, and aroma, and leaf size, all of which was important to consumers. Overall, the consumers preferred the seedlings that were grown under 200 micromoles. However, they preferred the size of the leaves, which were grown under 400 to 600 micromoles. Consumers obviously liked the larger size leaves, a moderate taste and aroma, that crisp texture, but they disliked the discoloration that occurred under higher light intensities, as well as the bitterness. Some of those potential impacts are that now we know that light intensity has a large impact on taste as well as consumer preference. And this may result in differences throughout the year, right? Especially if we're growing in greenhouses. Can we market basil as having a higher flavor profile, having stronger or more bitter, or one that's lighter for, let's say, salads? Future analysis that can occur are obviously market preference segmentation. So which parts of or which consumers may like more bitter basil compared to consumers that may like it more sweet. I know there have been several questions that have come out in the chat box that indicated, why did we look at the seedling stage? Well, it was going to be pretty difficult for us to look at the finishing stage within our various treatments. And so that's why we focused on the seedlings, but our hypothesis is that you would find very similar profiles if you were to finish the crop indoors. So with that, I'd like to thank all of our collaborators that helped us with this research, as well as undergraduate students and our technician. I'd also like to thank the following horticultural and grower organizations for helping with the study, as well as providing lighting, substrates, fertilizers, and our hydroponic systems. And with that, we can answer questions that you might have.